Okay, so how do we avoid D'Alembert's problem? How do we become like Necker, right? How do we actually make sure that we cover the entire sample space? This is where we're going to invoke what we call the fundamental principle of counting. And before I tell you what that is, I'm just going to show you using what we call a tree, an event tree. So let's think about taster 1. Now, taster 1 could be correct or incorrect. And in our model, we think with a 50-50 probability because everyone's just guessing, right? So taster 1 could be correct or incorrect. Now, based on that, if taster 1 is correct, taster 2 could be correct or incorrect, right? But even if taster 1 is incorrect, those same events can happen. Taster 1 could be correct or incorrect. So there's 4 different outcomes we see, where they're both correct, taster 1 is correct, taster 2 is incorrect, taster 1 is incorrect, taster 2 is correct, or they're both incorrect. So this is our entire sample space. And presumably each of these, in our model where everyone's guessing, each of these has a probability that's equal to each other, so it's 1/4, right? And what's the probability that one person gets it right but the other gets it wrong? We don't really care who it is. That would be these two added together, so 1/2, right? Just like the heads and tails case. Okay, so that's with just 2 people, right? And when we have 2 people, 2 people and 2 different choices, right? What we see is you could I sort of like to think of each like taster or each coin flip as a slot, right? A slot where something could happen, right? Here, 2 things could potentially happen. Here, another 2 things can potentially happen. So if you multiply them together, you get 4 outcomes, right? And so this should sort of remind you of like permutations, combinations, sort of. So, you know, it's sort of along those same principles, right? Because we're looking at how many different kinds of outcomes can we have. All right, so that's for just 2 tasters, and the world already gets a little bit complicated. What about if we had more tasters, like for instance, 3 tasters? I'm going to write this fairly small to help us out. So taster 1, still, they could be correct or incorrect. Taster 2 can then be correct or incorrect, right? And taster 3, for each one of these outcomes, can be correct or incorrect. Getting squished. All right. So when we count all these up, we have 1 branch here, another branch here, another branch here, another branch here, right? And so we have 8 different outcomes. So we have C, C, C. We have C, I, I. We have C, oh wait. I actually like to write it this way. There's sort of a trick for this. I'll show you my little trick. I'm going to write it over here to make it longer. We know that we have 8 different outcomes. The way that I do it is I know my first one, half of those have to be, for the taster 1, half of those have to be correct, half of them have to be incorrect. So half of 8 is 4. So there's going to be 4 where the taster 1 is correct and 4 where taster 1 is incorrect, right? Out of these 4, half of them, taster 2 has to be correct, half taster 2 has to be incorrect, right? But then that's the same case for these guys. Half of them, taster 2 has to be correct, half of them, taster 2 has to be incorrect, right? And then taster 3, we know that for each of these cases, because they're identical here, taster 3 has to be correct half the time and incorrect half the time, right? So correct, incorrect, correct, incorrect, correct, incorrect. Ta-da! And if you look, this is a systematic way of making sure that each line is different from each other, right? So we have CCC, CCI, CIC, CII, blah, 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 right? And the way that you could look at this is you have taster 1, taster 2, and taster 3. Each have 2 possible events, and there are 8 different outcomes. Now, for 4 tasters, it's going to be really complicated to draw the tree. So instead, I'm just going to do my little just finding out how many outcomes I have. So here I have 4 tasters. Each has 2 possible events, being correct or being incorrect, right? So that is 16 possible outcomes, right? And we know I can use this method where I might have, so half of 16 is 8, so C, 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 C. Oh, I'm not going to have space for this. Maybe I'll try to draw it a little bit smaller. So C, 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 C. So here's 8, and here's 8 eyes. More, okay. And then I'll draw the next one with blue. So I know that half of these, taster 2 has to be correct. Half of them, taster 2 has to be incorrect. So that's going to be 4. And then I'll go to black. And so now taster 3, half of the time has to be correct. Half the time has to be incorrect, right? So correct, correct. And finally, I'll go back to red. We just alternate. So hopefully, I remember having to do this for logic classes with true and false sometimes. Hopefully, your instructors won't ask you to do more than 4. 5 gets crazy too. But, it can be done. You just have to keep track that, roughly half of these have to be correct, half of these have to be incorrect. All right, so this is our 16 sample spaces, and each of them have a probability of 1 out of 16. All right, so where do probabilities actually come from? Well, one is that it comes from observed data. We actually look at real data in the world in order to figure out a probability. In fact, you might think that it's a 50-50 chance of having boy and girl, but actually observed data actually tell us that it's 51% chance of having a boy versus a girl. But, those probabilities might be affected by other things like preference for sons in other countries, things like that. All right, so the second thing is symmetry. Heads and tails is a really good example of symmetry. There's no reason for thinking that flipping heads is more likely than flipping tails, right? And whenever you have somebody who's guessing, so guessing on a multiple choice test, that invokes symmetry. What we mean by symmetry is not necessarily being the same on both sides, but being the same for each option, given that there's no reason to think one option is better than the other. And the final thing is subjective estimates. This one is the most sort of iffy. It's sort of like, how likely are you to get a good grade in this class, right? No one can actually tell you for sure. You just sort of have a feeling about, oh, it's very likely, it's not very likely, maybe this percent, maybe that percent, right? So those are pretty subjective, not really based on hard data. But since that's where probabilities come from, the question then arises, well, if we have some sort of probability model of the world, right, how do we know whether our model, our theory of the world, matches the real world? Because it would be sort of useless to have a model that's inaccurate and it doesn't match the real world, right? Well, here's where we invoke what we call the law of large numbers. What we assume is a reasonable fit to the real situation is we assume that when we have when we can compare the probabilities derived from the model with the probabilities estimated from the observed data. So if the observed data, if a lot of, or I should say, a lot of observed data, right? So if we have a lot of observed data and that matches with our model, then we would assume reasonable fit, right? And that's what we mean by the law of large numbers. The more data we have, the more we trust in that. The more we trust in that match, right? So if we had a match, but we only had a very, very small data set, then we wouldn't trust it. But the larger and larger our data set becomes, then the more we're saying, oh, okay, if it matches, that's pretty good. Okay, so remember, in D'Alembert's model and Necker's model, they predicted different probabilities for flipping of heads. So flipping of 0 heads, D'Alembert thought was 1/3, 1/3, and 1/3, and they all add up to 100%, or one probability of 1. In Necker's model, he thought these had a 1/4 probability, but a probability of just 1 heads is 1/2, so 1/2. And so if we actually flipped 3,000 coins, or you did it on a computer simulation, you might get data that looks something like this. 782 out of 3,000 came up with 0 heads, right? So I should say pairs of coin flips, right? 725 came up with 2 heads in a row, and about 1,500 came up with 1 head, and the other one being tails, right? And so when you look at the probabilities, you just take this number and you divide by the total, right? You see that we get these particular values. Do these match the Necker model, or do these match the D'Alembert model? Well, it's fairly easy to see that this actually matches the Necker model. So using the law of large numbers, we could say, the Necker model, it fits more with the real world than the D'Alembert model.